Hello everyone and welcome back to another video. Today we're going to go ahead and get started with RF3 for quadratic functions. Before we get going, let's take a look at a review of common factoring techniques. For these top three, we're going to go ahead and factor out the GCF of each of these polynomials. So recall that the GCF is going to be the greatest factor that can be essentially factored or divided out of all of the terms from each polynomial. So for example, if we take a look at this first guy, we can divide out an x from all three of these terms. So when I factor out this x, whatever is left on the inside here, we've got x squared minus 5x plus 1. We can check our work by going back and multiplying this x into each of the terms left on the inside of the brackets, and we will end up with the original polynomial. So go ahead, take a couple minutes, work through these next two examples. Next, we're going to take a look at factoring out a binomial factor. So really what we can think of is this section right here, this a plus b, that is a common binomial factor. So if we substitute in something like an x for the a plus b, we really have the same thing as 2x minus 3mx, and we'd end up factoring it out as x times 2 minus 3m. And that's really all we have. So if you were to do the same thing here, we're just going to factor out that a plus b to the front, and we are left with 2. And let's go ahead and change that to a blue color. So we've got a 2 minus 3m left over, which is really exactly what we have here. We have that x, which we now see as that a plus b. So go ahead, take a couple minutes, work through the next two on your own. So with these next three trinomials here, we're going to factor these out knowing that a is equal to 1, which means that we have a pretty quick shortcut. So we're really just looking for two numbers that multiply to 6 and add up to give us -5. So in this case, we can factor this out as x minus 3 and x minus 2. Take a couple minutes, work through the next two, and check your answers. For these next three examples, we're going to factor these using decomposition. So we can see here that a does not equal to 1, which means that in this case, we're going to take a times c. So we know a times c is equal to -30. And in this case, b is equal to a positive 13. So we want two numbers that multiply. So something times something gives you -30, and something plus something is equal to 13. So in this case, we have positive 15 and -2. So we can see that that kind of works out for us there. So we're going to go ahead and factor this using those two numbers. So 5x squared plus 15x minus 2x minus 6. We're going to go ahead and factor these out using grouping like we did in the previous examples. So we're going to factor out that 5x. We're going to be left with x plus 3. Factor out the -2 here, we're left with x plus 3 as well. And we have x plus 3 and then 5x minus 2. Take a couple minutes, work through the next examples on your own and check your work. Let's take a look at a couple more types of factoring problems. So here we can take a look at difference of squares. So a quick example is 4x squared minus 25. So we notice that both of these terms are perfect squares. So the square root of 4x squared is going to be 2x, because 2x times 2x gives us 4x squared. And the square root of 25 is just going to be 5. So we can actually factor this polynomial as 2x minus 5 and a 2x plus 5. So you can see here the only difference between our two binomial factors is one is a plus and one is a minus. Again, it doesn't really matter if you put them minus first or the plus first. They are both the same. One more quick example. Let's take a look at 12x squared minus 75. So we notice that neither of these terms are perfect squares. So we're going to go ahead and divide out a 3, and we're left with 4x squared minus 25. So we can see here that this guy is a perfect square trinomial, which is exactly what we had before. So just a quick little shortcut here, 2x minus 5 and 2x plus 5. So the last example of factoring review that we're going to do is a perfect square trinomial. So let's say, for example, we have a squared plus ab plus b squared. This ends up getting factoring as a plus b squared. On the other hand, if we have a squared minus ab plus b squared, this gets factored out as a minus b squared. So the last type of factoring review that we're going to do is a couple of examples of perfect square trinomials. So let's say, for example, we have 4x squared minus 20x plus 25. So we notice that this first term is a perfect square and this last term is also a perfect square, but we have a negative here in the middle. All we're going to do is we're going to take the square root of that 4x squared. We're going to put it at the front of both sets of brackets so that 2x goes to the front. The square root of 25 is going to be 5. So you got a 5 here and there. And because it's a negative right there, we're going to put a negative right there. So we'll notice that this middle term, that negative 20, well, where does that come from? That comes from going 2 times the square root of 4x squared, which is 2x, and from the square root of 25, which is going to be 5. But because it's a negative, we're going to put a negative 2 there in front, and that's where that negative 20x comes from. One more quick example. Let's say we have 16x squared plus 40x plus 25. Once again, this is a perfect square here and a perfect square there, except in this case, we have a plus 40x in the middle. So we're going to put a 4x and then plus 5 because of that plus sign, and 4x plus 5. So I missed a step here. Let's go ahead and put that 2x minus 5 squared there and the 4x plus 5 squared down here. For a more in-depth review of factoring, please go ahead and take a look at my Math 10C video for factoring polynomials. So taking a look at quadratic functions in vertex form, which is going to be our first topic, we're going to go back to talking about linear functions. So back in grade 10, we talked about linear functions, linear coming from the word line. So all of the functions that we looked at really were just straight lines. Now, if we're looking forward towards 20 level math, we're going to go ahead and start looking at curves. More in particular, we're going to look at quadratic functions. So in this case, if we were looking at a football being kicked, we'd actually start on the ground, it'd get kicked up, and it would kind of curve back down just like so. So this curved path is really just the foundations for the types of graphs we're going to study in Math 20-1. Let's go ahead and put this into practice. So for this example down below, we have a function that's modeling the height f of d of a football kicked over time, where d is going to be the horizontal distance from where the ball was kicked. So we have h of d is equal to negative 0.04 d squared plus 0.8 d. So we're going to go and sketch this on your graphing calculator using this type of window. So on your graphing calculator, really what you're going to be entering in is y1 is going to be equal to negative 0.04x squared plus 0.8x. So what these window settings really mean is that under your windows or window settings, we've got this is your x min. This 25 will be your x max, and this 5 is your x scale. On the other hand, for these three settings here, this will be your y min, This is your y max. And finally, this one is going to be your y scale. So essentially what these values do is they tell you what your minimum x or y value is, what your maximum x or y value is, and what your scale is going to be. So if we take a look at the x minimum, you'll notice that the x minimum is 0. So it shows up as a 0 right here. Your maximum x value is going to be 25, and your scale for each of the points on your graph is going to be in increments of 5. Same thing for your y min, y max, and your y scale here. So if we were to go ahead and graph this, we're going to end up with the shape kind of looks like this. So at a distance of 10, we're going to get a height of about 4. When it gets kicked from the ground, you obviously have a horizontal distance of 0 right at the beginning. And when it finally reaches the ground again, we have a horizontal distance of 20, and you're going to have a height of 0 because it's back on the ground. So if we were to go ahead and sketch this, I'm going to go ahead and add 2 more points, one right there and one right there. We'd end up with a nice curve just like this. So what's so different about this type of graph compared to a linear graph? Well, it makes a shape. This U shape here is what we call a parabola. And really what's so different about this equation compared to a linear equation is we can see that here we have a squared. So anytime we see some sort of square in the equation, really have a degree of 2. And since it's a degree of 2, we call this a quadratic function. So for this next section, we're going to go ahead and use Desmos, which is a very handy online graphing calculator. So that's desmos.com to help us figure out this next section. So we can see here that we've got our equation set up. Y is equal to a times x minus p squared plus q. We're going to go ahead and take a look at some of the parameters set. So the first thing we're going to do is play around with the a value. So you can see maybe starting at 1 here. So we've got our parabola looking like that. And as I slowly increase the slider towards the right and our a value gets larger and larger, you can see that this parabola starts to narrow. Okay, and as we start to decrease the value again, it starts to get wider and wider and wider. Up until we get to a certain point. So you can see here it gets quite wide over at 0.1, and then all of a sudden it becomes a flat line here at 0. Now that becomes a flat line because in this case when a is equal to 0, you have 0 times anything. We're going to end up essentially with whatever value our q is. So you can see here 0 times, so this would be 0 times whatever here is going to be 0, and then plus q. So in this case, if q is 3, then we end up with a horizontal line with a y-intercept of 3. Now, obviously that's not very fun for us. So we're going to go ahead and go past 0. We're going to go towards the negatives, and we can see that we are flipping, right? We're flipping from this graph opening upwards when it's positive to this graph starting to open downwards when that a value becomes negative. Okay, and we see again as that negative value grows larger in magnitude, we can see it gets narrower and narrower and narrower. Okay, so let's reset this value to 1 here. And we're going to go ahead and play around with this p value. So right now p is equal to 1. Okay, and we can see here that our vertex, our lowest point of our parabola, remember our U-shaped curve, is at 1, 3, so an x value of 1 and a y value of 3. We're going to go ahead and move this p value. Okay, so let's go ahead and move that p value to 2. And we notice here that the vertex has now changed to 3. And let's go ahead and move this to maybe a 5. And we can see here that the x coordinate is now a 5. So we can go ahead and make the assumption that this p value affects whatever that x coordinate of our vertex is going to be. If I were to go in the opposite direction, let's say p is equal to, let's say 0 first. It's going to be right there on the y-axis. And as I start to move towards the left, where let's say p is equal to -2, we can see that we have now shifted 2 units on the negative. So now we're at -2, 3. Now taking a look at our Q value, we have a Q value of 3 in this case. Well, if we start to move it up and down, you can see that when we move this Q value to 4, okay, now our vertex has a Y coordinate of 4. And if we move it to maybe, let's say a 7, it's now shifted up to a 7. Okay, and if we were to move this down, and let me shift my graph a little bit, this becomes, when Q is a -2, we can see that the Y value of your vertex is also a -2. So if we look at a quick little summary here, we're going to go ahead and summarize our parameters A, P, and Q. So if we're looking at A, really it talks mainly about two things. First of all, the direction of the opening, and second, the width of the parabola. So if our A value is positive, then our graph is going to open upwards. So it's going to look something like this. If our A value is negative, our graph will just open down just like that. Looking at the width of the parabola, we have really just two situations. If we have A is greater than 1, or if A is less than -1, then your graph becomes narrower. If A is between 0 and +1, or between -1 and 0, then your graph just becomes wider. Taking a look at our second parameter, we have our p-value. So our p-value really just tells us about the horizontal translation. So the amount of units that the graph moves towards the left or to the right. So some key things to note here is that if your p-value is positive, then your graph is going to move p units to the right. And if p is negative, then your graph is going to move p units to the left. So what that's going to look like, because our equation is x minus p, right? So if p is positive, then we'll have something like x minus 2, and this means 2 to the right. Now, on the other hand, let's say that p is negative. Let's say that it's x minus a -2. Then in your equation, you'll actually see x plus 2. So if you see x plus 2, this means that we're going to move 2 to the left. Looking at our last parameter, we have now our Q value. So our Q value really just tells us about our vertical translation. So this one's pretty straightforward. If Q is positive, then your graph is going to move up Q units. And if it's negative, it's just going to move down Q units. So if we have plus 2 at the very end here, then we're just going to go 2 up. And if it's minus 2, then we're just going to go 2 down. One other thing to note is that for your P and Q values, P gives you your X coordinate of your vertex, and Q is your Y coordinate of your vertex. So basically at the vertex, which is this point right here, really just have P, Q as your X and your Y value. So I've been using a lot of vocabulary that you may or may not have caught. So let's take a look at a quick summary of what we've discussed so far. So a quadratic function is really just any function f of x with a polynomial of degree 2. So the most basic one that we're going to look at in this outcome is f of x is equal to x squared. So we can see that degree of 2 really just means that we have an exponent of 2. Next, we've got the parabola. Remember, it's not a parabola, it's a parabola. It's a symmetrical curve of the graph of a quadratic function. So really, it's just any U-shaped curve that looks like this or looks like that. Could be narrow, could be pretty wide. Just depends on the function itself. For the vertex of a parabola, it's really just going to be your lowest point of your graph if it opens upwards. So if it looks like this, we've got a nice curve there, and your vertex is going to be right here. And then if it opens downwards, it's going to look something like this, and your vertex will be right there. So that vertex will be called different names depending on if it opens up or down, or if it's your minimum or maximum point. So your minimum value is going to be your Y coordinate of your vertex. So if we're taking a look at this guy right here, whatever your PQ is, your minimum is going to be that Q value. On the other hand, the maximum value is going to be your Y coordinate of the vertex if the parabola opens downwards. So this guy right here will have PQ. That's going to be your maximum value there. Now the axis of symmetry here really is just the line that divides your graph into two equal parts. So really just the line splitting the parabola down in the middle. The important takeaway here is going to be your x coordinate of your vertex, which just gives you your equation of your axis of symmetry, which is really just x is equal to p. So for example, if we take a look at this guy here, I know we haven't done a lot of work sketching so far, but if we were to quickly make a little sketch, x minus 3 plus 1 implies that we'd have something that would look like this. So we said if your a value is between 0 and 1, it's going to be a little bit wider. This positive p value, so in this case p is equal to 3, and let me rewrite that, p is equal to 3, q is equal to 1. So that means that we have our vertex at 3, 1, and because our a value is positive, we're going to open upwards. So 3, 1 is probably somewhere, well, let's say about there. And because it's a little wider than normal, let's do something like this. And since our p-value is 3, your equation for the axis of symmetry is x is equal to 3. So we're going to go ahead and draw your axis of symmetry right there and just label that x is equal to 3. So we're going to go ahead and explore the vertex form of the equation of a parabola. So we have y is equal to a times x minus p squared plus q. Remember, your vertex comes from your p and your q values. So a couple quick notes before we sketch the graph of a quadratic function in vertex form. We want to make sure that we start off with your vertex. It's going to be the most important part. We don't always have to draw on the axis of symmetry, but it helps us out if we're sketching all of the points of the graph. Typically, I would suggest about 2 to 3 on either side of your axis of symmetry. We want to go ahead and use the equation to find one other point on the parabola. So typically we start with the y-intercept, and then we move on from there. And then we want to try to find corresponding points that go from one side to the other. And then we're going to go ahead and draw a parabola through those points that you found. So for this first example, let's go ahead and take a look at our function. So we've got f of x is equal to 1/2 x minus 4 squared minus 3. So if we're looking at our vertex here, the first thing that we want to do is identify your p and q values. So in this case, your p value is 4. Oh, let me write that a little bit neater. Your p value is 4 and your q value is -3. So that means that our vertex pq is just 4, -3. So 4, -3 means that our vertex is going to be 4, -3. It's going to be right there. Second thing that we want to take note of is your direction of opening. So remember, your a value tells us about our opening. So in this case, your a value is a positive 1/2, which means that it's going to open up. So before we go ahead and talk about the domain and the range, I want to talk about the axis of symmetry. So for us, the axis of symmetry is going to be at x is equal to 4. Remember, your p-value is 4. So our equation of the axis of symmetry is x is equal to 4. So I'm going to go ahead and draw a vertical line that kind of cuts through the middle there. And from here, we're going to go ahead and plot a couple points and see what we end up with. So let's say, for example, we have f of 0. So that means that my x value is 0. And we're going to see what happens when I plug in a value of 0 there. So I have 0 minus 4 inside the brackets, squared minus 3. So I have 1/2 times -4 squared minus 3. So this leaves me with 1/2 times 16 minus 3. So 1/2 of 16 is 8. 8 minus 3 is 5. So that means I have a point at 0, 5. So my first point goes there. So again, going back to this, this point right here using your axis of symmetry, we just use our equation to find a point on the parabola. So we found 0, 5, and we're going to draw the corresponding point that is equidistant, right? The same distance from the axis of symmetry. So what that does for us is we can see here that we are 1, 2, 3, 4 units away on the left-hand side. So we're just going to mirror that same thing on the right-hand side. So 1, 2, 3, 4 units on the right-hand side of it. And we're going to go and draw that point. So repeating this same process for a few more x values here of your choice. In this case, a good one is going to be an x value of 2. So if we have an x value of 2, then we end up with a point here of 2, -1. We're going to go equidistant rather from the axis of symmetry, and we're going to put a point right there, and we can actually draw a nice smooth line, or as smooth as possible, through those 5 points, and we can actually just go ahead and extend this line all the way up. So it's going to look something like that. So now that we have a rough sketch of what our parabola is going to look like, we can go back to the domain here, and we can see that whatever values of x we put in, whether we put in x is -10, x is +1000, there's really no restriction because this U shape is going to continue forever towards the left and the right hand side. So for us, the domain is going to simply be the set of all x values such that x is an element of the real number system. On the other hand, if we're looking at the range, okay, we've got the set of, well, it's not a great bracket. We've got the set of all y values, and this is tough to do on a tablet, the set of all y values such that, okay, taking a look at our y values here, we can see that because it opens up, we're going to have a minimum value. So all of your y values have to be greater than this -3 here. So y has to be greater than or equal to -3. And as long as it's greater than or equal to -3, y can be an element of the real number system. So now that we've gone through an example together, you can go ahead and pause the video, take a few minutes to sketch out this function here, and then unpause and check your work. So the next thing that we want to do is determine the number of x-intercepts by examining the a and q parameters to help us figure out exactly how many x-intercepts we're going to end up with. So in this first example, we have y is equal to -3 times x plus 2 squared plus 1. So in this case, a is equal to -3. So that means that your parabola will open downwards. Your value of p and q, so since p is equal to -2, remember it's going to be x minus a -2, which gives us the x plus 2. So p is -2, q is equal to 1. That means we have a vertex at -2, 1. So if we were to quickly sketch this graph, -2, 1 is going to be in this quadrant right here. So -2, 1 means we're going to have something there. And because it opens downwards, we're going to quickly sketch that graph. And we have something that looks like that. And we can see that we have 2 x-intercepts. So here we'll pause the video. You can take a few minutes to work through the next 3 examples here on your own, and then unpause and check your work. So in this section, we're going to try to figure out the equation of a quadratic function in vertex form if we are first given the graph. So in the first example here, we're going to go ahead and identify the vertex, which in this case is going to be 6, -4. So 6, -4. That means for us, p is equal to 6 and q is equal to -4. From there, we're going to start off with our vertex form equation, a times x minus p squared plus q. And we're going to substitute in our values of p and q. So we've got x minus a positive 6 squared, and then we have -4. So that's where those 2 values come from. The next two things that we need to figure out is we need to figure out your xy along with your a value. So we're going to use a point. So in this case, some of the easiest points to use will typically be your y-intercept. So in this case, 0, 8. So that means that 0 is going to be x and y will be 8. So now we're going to go ahead and substitute those in. So instead of y equals, we have 8 equals a times 0 instead of x minus 6 squared minus 4. So we have 8 is equal to a times negative 6 squared minus 4. And we'll have 8 is equal to negative 6 squared, which is negative 6 times negative 6 gives us 36a minus 4. We're going to add 4 to both sides. So 8 plus 4 gives you 12, and negative 4 plus 4 gives you 0. So 12 equals 36a. And then finally divide both sides by 36. So 12 over 36 is equal to a, which simplifies to 1/3. So from here, we end up with a final vertex form of y equals 1/3 x minus 6 squared minus 4. So we want to keep the y and the x as such, right? Because our key things were to find three values. Your a value, which we just solved for. We found your x value of your vertex. And we also have your y value of your vertex. So putting it into this format means that really for any point that's on this line, if we put any type of x value into here, we'll be able to solve for another y value that will give us a point on this parabola. Here you can go ahead, pause the video, and try to find the vertex form of this graph on your own. Once you're done, you can unpause and check your work. So the next part of this lesson is really just an opportunity for you to apply what we've just learned in more realistic situations. In this first example, we've got the Lions Gate Bridge in Vancouver that we're taking a look at. And we've got the deck of the bridge being suspended from two main cables that are attached to two supporting towers. Between these towers, the main cables take the shape of a parabola as they support the weight of the deck. The towers are 111 meters tall relative to the water's surface and are 472 meters apart. The lowest point of the cables is approximately 67 meters above the water's surface. The first thing that we want to do is to model the shape of the cables with a quadratic function in vertex form. So remember, vertex form was just simply y is equal to a times x minus p squared plus q. And we want to try to figure out how do they end up with this 236.44, x and y value right here. The first thing that we want to kind of identify is that we are either going to set up our origin. Oh, that's not very neat. Origin at the vertex. So what that means for us is you guys can see this x and y axis that are set up here with our origin right there. Alternatively, what you could also do is you could set up your origin on the left or right edge. So you can set it up that you have your origin here, and then really you just have a parabola coming down towards this way. But personally, I prefer to set up your vertex right there, or your origin right at the vertex, because we're going to work with 0, 0, and working with 0, 0 is a fantastic thing to do, as you're about to see here. So we're going to go ahead and take a look at how to come up with our quadratic function in vertex form. So step number one is we're going to go ahead and start with vertex form. Y is equal to a times x minus p squared plus q. And the reason why we want to start off with our vertex is since we know that p is equal to 0 and q is equal to 0, we're going to go ahead and substitute those into our equation here. The second thing that we're going to use is we're going to use one of these 2 points. We're going to go ahead and use this 236 and 44. So let's just call this X and Y, and we're going to plug those values in here as well. So we've got 44 is equal to our A value, which we're trying to find out. And our X value we said was 236 minus 0 squared, and then plus Q, which was plus 0. From here, we're going to go ahead and simplify. 44 is equal to A times 236 squared plus 0. Doesn't really change anything. So we get 44 is equal to 55,696 A. Then we divide both sides by 55,696, and that's going to be equal to our A value. So we can see here that since our A value is positive, then our parabola opens up, which it does. We can actually simplify this a little bit more. Divide both the top and the bottom by 4, or factor out of 4, and we get 11 over 13,924, and that gives us our A value. Now what we're going to do with this A value is put this back into our vertex form. So we know that we have Y is equal to our A value, 11 over 13,924. We have X minus P. So in this case, P was 0. So X minus 0 squared plus our Q, which was also 0. So we can see pretty quickly, this is perfectly fine as an answer. It tells us that our vertex is at 0, 0. If you'd like, we can go ahead and actually simplify this to 11 over 13,924 X squared. Now to answer the rest of the question, how do they get this point 236, 44 in the diagram? So we're going to take a look at some of the original information that they gave us. So we can see here that the towers are 472 meters apart. And the key here is understanding that since our X, or rather our Y axis, gives us our axis of symmetry, just kind of naturally breaking that in half, we can see that this essentially evenly divides the bridge in half. And if we go 472 divided by 2, that gives us 236. So that means that each half of the cable ends up going a horizontal distance of 236 units either way, or rather meters either way. So you can see that we end up getting the 236 from that. And then where does the 44 come from? Well, we know that since each tower is 111 meters tall roughly, and we know that from the bottom of the cable to the water surface is 67, we simply go 111 minus 67, and that gives us a grand total of 44 meters. So that's how they ended up with 236, 44 as one of the points on your parabola. For this next question, we're going to go ahead and determine the height above the surface of the water of a point on the cables that's 90 meters horizontally from one of the towers, and express our answer to the nearest hundredth of a meter. So the key things to note here is, since we're looking at something that is 90 meters horizontally from one of the towers, basically we are just going to move 90 meters this way from at least the right tower, which means that somewhere over here we're going to end up at 236 minus 90, which gives us 146. So our X value for this point is going to be 146. And we aren't really sure what that height is, so we're just going to call that Y. So we're going to go and use this point, 146 Y, and we're going to plug this into our vertex form that we found a little bit earlier back up here. So we get Y is equal to, we're trying to find out what that Y value is. And the whole reason why we are using this X value of 146 is we're going to plug it into this guy here. So Y is equal to 11 over 13,924 times 146 squared. So we plug that in. I'm not going to write the entire thing down. We're going to plug that into our calculators, and we get about 16.84. Okay, so therefore we can state that the height is 16.84 meters. So for this next question here, we're going to take a look at the Gateway Arch in St. Louis, Missouri. It's stated that it is 630 feet tall and 630 feet wide. So before we actually draw or get into this question, we want to be able to identify the two different ways we could look at this. Typically, we're going to draw our Cartesian plane somewhere. So you can see that the arch comes up like this. That's our parabola in this case. And we can actually draw our y-axis looking something like that and our x-axis. So then we essentially have our parabola starting here at 0, 0 and kind of arching down that way. So that's option number one. Option number two that we could potentially use as well is, remember in the previous question, we said that we could use our vertex as the origin. And really, if our vertex is the origin, we are drawing it, or we're starting our Cartesian plane just like that. And that parabola actually comes underneath the x-axis. So a couple different ways that we could do it, right? So it's going to look like, kind of like this if we decide to go that method. I don't really like going that method for a real life question like this. And the reason why is because we're going to have a lot more positive values if we kind of keep what we originally had in mind for this particular example, at least. So let's go ahead and write a quadratic equation that's going to model this archway here. So once again, starting off with our vertex form, y is equal to x minus p squared plus q. We're going to go and label certain parts of this archway. So the first one I'm going to label is the origin, which is going to be just 0, 0. We know that it's 630 feet tall. So we know that right here in the middle, our vertex, we're going to have a y value of 630. Before we get to the x value, we're going to look at the second number here. We know that it's 630 feet wide. So we know that from here to here, the origin, until the next point of contact down over here, it's going to be 630 feet, essentially. So this gives us 630, 0. On a previous page, we talked about the vertex of your parabola essentially splitting both sides equally. So if we know that both, or rather, this entire parabola goes from 0 to 630, splitting this right down the middle yields us an x coordinate of 315. So using that 315 and 630, we now have our p and q values. Using one of these 2 points down here, we're going to find our x and y. And of course, mathematicians love a good origin point, right? So we've got x and y as, or 0 and 0 as our x and y values. So let's go ahead and substitute those in. So we've got 0 is equal to our a value, which we don't know yet. 0 is equal to a times 0. Then we've got minus p, which in this case is 315. And we're going to square that. And then we're going to add 630. So let's go ahead and simplify a little bit. I'm going to subtract 630 first to make things a little bit easier. We're going to square that negative 315. So that means negative 315 times negative 315 gives me 99,225 times a. Our last step here is to divide both sides by 99,225. So negative 630 over 99,225 is equal to my a value. And we're actually going to go and reduce this a little bit. And we end up getting a is equal to negative 2 over, and let's make that negative a bit more pronounced, negative 2 over 315. So this kind of reinforces the fact that our parabola is going to open downwards because our a value is negative. So cleaning everything up, we're going to go ahead and put this in vertex form. Y is equal to negative 2 over 315, x minus our p value, which once again was 315, squared plus our q value, which is 630. Second part of this question says determine the height of the arch that is 200 feet from the outer edge. So 200 feet from the outer edge means that we can actually look at one of 2 points here. We can actually look at 200 feet in from the start. So we're going to have 200y, or we're going to have 200 feet back from 630, which means we have 430, and then some y value here. So let's go ahead and use the second point, 430 and y as our xy. So let's write that down here, 430 and y, that's my x, and obviously that's my y over there on the side. So plugging this into our formula, y is equal to -2 over 315, and our x value we said was 430. The y we just kept the same because that's what we're trying to solve for. 430 minus our p value, which was 315 squared plus 630. So plugging this all in, we're going to simplify a little bit. We end up getting 17,390 over 63, which gives us a grand total of 276.0 when we round it. So therefore, the height is 276, it doesn't say in tenths, but 276 feet. So for this next part here, we're going to look at expanding our vertex form, or sometimes called standard form in some texts, into general form. So remember, general form from Math 10C was just y is equal to ax squared plus bx plus c. So we're going to take a look at all of this and see how that works together. So let's go and compare the two forms. So we've got vertex and general form, and the types of characteristics that we can figure out or use to help us figure out certain characteristics of each graph. So with vertex form, we've already talked about the vertex, or the axis of symmetry rather. So x is equal to p, that just comes straight from your p value. And your vertex is just your p and q. So just p and q. Very, very straightforward. Vertex form tells us what the vertex is, which is fantastic. In general form, though, this is where it gets a little bit nutty. With the axis of symmetry, taking a look at our equation here, we have x is equal to -b over 2a. All right, so the b and the a just simply come from our equation in general form. So let's say, for example, we have y is equal to, 3x squared plus 5x plus 1. In this case, our x, or our axis of symmetry, would just be x is equal to, well, in this case, we have -b. So -b would be -5 over 2 times 3. So we get -5 over 6, and that's going to be our axis of symmetry. So that's how we'd use that portion there. For the vertex, we know already what our x coordinate is going to be. It's just going to be -b over 2a. And this 4ac minus b squared over 4a, that's going to look super, super complicated. But really, both of these parts here are really just derived from general form using a method called completing the square, which is what we're going to explore later. For the time being, just take it at face value. These a, b, and c values come straight from whatever equation is already given to you. So again, just to reiterate, depending on your situation, you might decide to change from one form to another. Just to make your life a little bit easier, you can use either one really to describe all of the characteristics of a given parabola, but obviously some tools are better for certain situations. So really quickly here, let's do a review of how we would expand from vertex to general form. So this x minus 4 squared, remember, whenever we square a binomial, x minus 4 squared, this is the same thing as x minus 4 times x minus 4. So x minus 4, we're going to go ahead and use the distributive property x times x. We're going to go ahead and multiply those two guys together, which gives me x squared. I'm going to multiply these two together. X times -4 gives me -4x. We're going to do the same thing with that second term. -4 times x gives me -4x. And then -4 times -4 gives me a positive 16. So once I simplify everything, x squared minus 8x plus 16. So going ahead and simplifying this, we have y equals 3 times, what we just found there, x squared minus 8x plus 16, and we're going to add 5 to that. So we get y is equal to 3 times x squared, so we get 3x squared, and then 3 times negative 8x rather, negative 24x, and then 3 times 16 gives me 48, and 48 plus 5 gives me plus 53. You might want to take a second, pause the video, and try out the second one on your own, and then unpause, check your work afterwards. So this guy will have negative 2x squared minus 4x minus 21. So our first example here, we're given the graph of the function f of x is equal to x squared plus 4x. We're going to identify some characteristics. First of all, the direction of opening. So in this case, we know that our a value is just equal to 1. That's a 1x squared. So that means that our direction of opening is up. And it's very obvious. We already know that's going to open up. Your vertex is going to just come from this point right here. We don't need any fancy formulas. So we've got negative 2, negative 4. So negative 2, negative 4. Our maximum or minimum value, in this case, we have a minimum value because it is opening downwards. We have a minimum of negative 4 when x is equal to negative 2. And let's make that a little bit neater. When x equals negative 2, slightly neater. Your equation of the axis of symmetry is just x is equal to negative 2, right? And that axis of symmetry just comes straight down there. Your x and your y-intercepts, we haven't talked too much about x and y-intercepts yet, but your x-intercepts are when your graph crosses the x-axis. So right here we have an x-intercept of, we have 2 of them. We have negative 4, 0, and we have 0, 0. For your y-intercept, it happens to also be the same thing as your as one of your x-intercepts. So we have y-intercept of 0, 0. For your domain and range, we can see that this parabola would continue indefinitely towards the left and the right. So we've got your set of x such that x is an element of the real number system. And with the range, we have a minimum value. So just to give a bit more a context on how we'd set up range, because I noticed that a lot of students struggle with domain and range. So the setup for your typical range might look something like this. You have y such that we're going to have your minimum value here. And typically we're going to have less than or equal to. So again, this is kind of contingent based on if you actually have a point existing there or not. So it's either going to be an underline or not underlined. But for us, in this case, it's going to be underlined because there is something at every point here. And then y is going to go right in the middle. Let's do that in black. So y is going to go in the middle there. And your maximum value is going to go right there. And we're going to have y as an element of the real number system. So typically it's going to look something like this. But for our particular example here, our range, so once again, setting us up, y such that we have a minimum value. Okay, so our minimum value here is negative 4. So following that same setup, negative 4 is less than or equal to y. We don't have a max value, so it's going to look something like this. And y is an element of the real number system. I'm going to maybe spend hours and hours practicing these curly braces here because I am awful on a tablet. So at any rate, if you write it like this, you will never be incorrect, although this does look a little bit clunky. Typically, we do want to write it something like this, so it reads out a little bit more naturally. Y such that y is greater than or equal to negative 4. Notice that the only thing I did was I moved the y over to that side, and the negative 4 back over onto this side, and we flipped our inequality sign here in the middle. So this reads out a little bit more naturally. But if you need a format to kind of follow, this is perfectly fine down here, but this one up top reads a lot more naturally because in English we do like to read from left to right. So on this page, we're going to talk a little bit about how to use technology, or more specifically graphing calculators, to help us find different characteristics of a given function. Now, for those of you with a TI, you're kind of in luck with these instructions, because these instructions are for TI-83s or TI-84s in particular, or plus CE, TI-84 plus, whatever version you have, they're more or less all the same. But luckily for everyone else, I'm a Casio guy, so go Team Casio. So I've got this emulator here on the side that we're also going to utilize to help us figure out the different characteristics for our example here. So before we get started, let's fire up your Casio or your TI in whatever case you have. And your Casio might look kind of like this. We're going to hit the menu button, and we're going to go down to graph, and I'm going to press EXE to get into there. And we're going to type in our equation. So y is equal to 2x squared. So the x button is right here. So x squared minus 8x plus 5. And we're going to press enter here. And you can either press draw, which is F6, or you can just press enter again. Whoops, missing something there. I can't do that. I missed my 5. So we're going to go, things are happening. Let's go back into it. So we're going to go to the end here. I'm going to go plus 5. And then we're going to go ahead and draw this function. So we get something that looks like this, which is great. And we can use that to help us figure out the direction of the opening. Now, this is just a bonus because hopefully all of you can see here that since your A value is 2, it's going to open up anyways. Okay, and we can confirm that with our graphing calculator as well. For your minimum or maximum value, we're going to go and use the Casio's functions. So for any of the Casio people, we're going to go to gsolve. You can see this gsolve right there, and press that F5. And the cool thing about this is that we don't need to do the second trace minimum stuff, okay, on a TI. So let's go ahead on the Casio first. So we know it's a minimum, so all I'm going to do is hit minimum, and look at that. It jumps straight to it. Okay, so we've got 2, -3 as our vertex, right? But we're looking at our minimum or maximum value. So for us, we have a minimum of -3 when x is equal to 2. Your vertex here is simply 2, -3. Your axis of symmetry is just x is equal to 2. And before I forget, what are you doing on a TI instead? So of course I can't show you guys on here, but essentially what the TI wants you to do is when you go second trace minimum, you're gonna move your cursor somewhere here to the left side of the parabola. Okay, and you're gonna press enter. And then that's when it said, previously it says left bound. And then once you press enter, it's gonna say right bound. So you're gonna go to the right-hand side of the parabola here, and you press enter. And then it's gonna ask you if you want it to guess. And obviously you do want it to guess, and you press enter one more time, and you get 2, -3 as that vertex. So essentially the left and the right bound is just setting a boundary or kind of a restriction for what you're looking at. Okay, so the left bound and the right bound really just says, okay, I'm looking between this point here and this point for my minimum or maximum value. And that's why I do like the Casio a lot better. There's a lot less finicking around with the buttons. You literally just press gsolve and you just press minimum, and out pops your answer. So moving on to x-intercepts, again, another big win for Team Casio, because I'm just gonna press gsolve here. And we can see that we've got, with our 2 x-intercepts, we've got 1 here and 1 there. We're gonna hit root. So root is really just another way of saying your zeros of a function, or where your y value is equal to 0. So your root, you got 1 there. So you've got a 0, okay, or x-intercepts, or 1 x-intercept right there at 0.77 roughly, or if we round it, 0.78. So let's go ahead and write that down. So we have 0.78, 0.78, 0.78, 0.78, 0. That was my first one. And then to find the second root, all we need to do is press the right button. So we've got 3.22 comma 0. And would you look at that? Look how easy it is on a Casio. Now, obviously I'm not sponsored by Casio, but hopefully you guys can see that there's good reason why plenty of math teachers enjoy using Casio calculators quite a bit more. Again, for the TIs, it's really not that bad, honestly. We just go second trace 0, and we're gonna do that twice, okay? So when I say do that twice, we're gonna do it first for the one on the left. So essentially what's gonna pop up on your TI is you're gonna have a little cursor pop up kind of over here, or you want it to go over here. And you know that your x-intercept's here. So for your left bound, you wanna go somewhere to the left of where my cursor currently is. So you wanna maybe put your cursor right there. So that'll be your left bound. You press enter. And then it's gonna say right bound. So we're gonna come somewhere down over here to the right, and we're gonna press enter. And it's gonna say guess, and it's gonna guess, again, this point right here, 0.76 and 0 as your first x-intercept. And once again, when we go second trace 0 again, so second trace 0, you're gonna have your cursor appear. And because we're trying to find this guy right there, we want your cursor now to be positioned somewhere here to the left. So you want your cursor to be somewhere down over here. You press enter for your left bound, and then for your right bound, you want to scroll up over here. So your cursor is maybe up over here. For the right bound, you press enter, it says guess, and it guesses this point right here, 3.220. Okay, and then for your y-intercept, on a TI, you're just gonna press second trace value and just enter x is equal to 0. For a Casio, it's pretty simple as well. All we're gonna do is we're gonna press F5 again for G-solve, and right here we've got y-intercept. We're just gonna press F4, and we have a y-intercept of 0.5. So 0.5 is your y-intercept. For your domain and range, we're gonna see that your graph is gonna go infinitely towards the left and infinitely towards the right. So we know that we have x such that x is an element of the real number system. And then for your range, we already talked about your minimum value of -3. So we can state that your range is y such that y is greater than or equal to -3, and y is an element of the real number system. So for this next section, we're gonna even out the playing field a little bit for doing this algebraically. Direction of opening, we're just gonna look at the a value, and I'm gonna use a nice teal in this case. I think that's teal. Turquoise, I've been told I'm maybe slightly colorblind. But we've got our direction of opening, which in this case is going to be upwards because a is equal to 1. Okay, so since a is equal to 1, our direction of opening is up. Your vertex coordinates, we're going to use x is equal to -b over 2a. So in this case, we have x is equal to -6 over 2 times 1. So in this case, we have -6 over 2, which is -3. So that means that x is equal to -3. And we're going to substitute this back into the equation to find y. Okay, so we've got y is equal to -3 squared plus 6 times -3 plus 5. So we have y is equal to -3 squared, which is 9. -3 times -3 is 9, minus 18 plus 5. So we get y is equal to -9 plus 5. So -9 plus 5 is -4. So our vertex is -3, -4. So obviously there's a bit more work involved when it comes to doing this algebraically. Your maximum or minimum value, we know that since it's opening up, we're going to have a minimum value in this case. So we know what our vertex is. We know it's going to have a minimum value of -4 when x is equal to -3. Our axis of symmetry is just x equals -3. To find the x-intercept, we're just going to factor your equation here. Okay, so with x squared plus 6x plus 5, I'm not sure if you remember from the beginning of this lesson here, we have y is equal to x squared plus 6x plus 5. We're going to look for two numbers that multiply to 5 and add up to 6. So in this case, we have x plus 1 and x plus 5. Okay, so from here, we haven't done quadratic equations yet at this point in the semester. But really all we're doing is just looking at what happens, what will make our y value equal to 0, right? Because remember, your x-intercepts are going to be anywhere where your graph has a y value of 0. Okay, so if we know that 0 has to be equal to x plus 1 and x times x plus 5, right? We have two things that are being multiplied with each other. One thing here and one thing there. The only way that we get a 0 product is if x plus 1 is 0 or if x plus 5 is equal to 0. And what's the only way to make this first binomial be 0? Well, we have from here, x is equal to -1, right? Because if I have -1 plus 1, that gives me a 0. So 0 times anything is 0. And from the second binomial factor, well, in this case, x would have to equal to -5 because -5 plus 5 gives me 0. So you've got two x-intercepts here, -1, 0. And then we also have -5, 0. Now, this might seem super confusing just because we're doing it at kind of a weird juncture here. So don't stress too much if you don't quite understand that setting your equation equal to 0 will give you your y-intercepts. Or x-intercepts rather, we're gonna go ahead and work through that in more detail later on. Your y-intercept, we're just going to set x equal to 0 and find your y value. So pretty much all we're doing is we're going to put a 0 in for x. And then basically we've got y equals 0 squared plus 6 times 0 plus 5. So 0 plus 0 plus 5. So we get y is equal to 5. So we got 0, 5 as our point for the y-intercept. Last but not least, I hope you guys can probably see that your domain for pretty much every parabola we're going to work with is x is an element of the real number system. And since we have a minimum, we've got y such that y has to be greater than or equal to, in this case, we've got negative for y as an element of the real number system. So for this last portion here, you guys will get an opportunity to try this out on your own. So feel free to pause the video, take a few minutes and work through this using your graphing calculators. And then by doing it algebraically, then unpause once you're all done and check your work. So one thing to note is that even if you are required to show all of your work algebraically, you can still feel free to check using a graphing calculator, and that's going to be a really good tool to verify that you've done things correctly, even on some sort of test or assessment. That's going to do it for this video. We're going to go ahead and look at completing the square and applying some of these graphing calculator tools and methodology in the next video. So once again, I hope you guys enjoyed the video and I hope you learned something. Thanks again for watching, and I'll see you guys all in the next video.